Let's begin. We were talking about radiation. Heat transfer by radiation. We got heat transfer by conduction, heat transfer by convection, and last of all, heat transfer by radiation. And heat transfer by radiation, we talked about this idea. That everything is emitting radiation of some frequency. These are electromagnetic waves. We'll be talking about electromagnetic waves later in the course. And electromagnetic waves have a frequency. Here's a high frequency. Here's a low frequency. There's a vibrational frequency to waves. And that vibrational frequency to the waves is directly proportional to the temperature. The temperature of the sun is enormous, and therefore we have an enormous frequency. So high a frequency that it activates the optical system in your eyes, and we call it light. That's very, very high frequency. Millions of billions of cycles per second. Little vibrations. Very, very high frequency. High frequency because the sun's electrons are shaking at high rates. We're going to learn later on, if you take an electron and shake it back and forth, you'll get a wave in space that will shake back and forth at the very same frequency. So it stands to reason something of a high temperature with a lot of molecular motion, okay, a lot of charges moving, that high temperature would give you a high frequency. So this is not counterintuitive. Sometimes we learn things that are kind of a little bit against common sense, and we have to look a little deeper till we find out, hey, it fits after all. This one we don't. It makes sense that a high temperature would emit a high frequency. If you take a piece of metal, right now, you guys can all see this. You're seeing this piece of metal because light's being reflected from the metal and goes to your eyes. But if I turned all the lights out, you wouldn't be able to see this metal. But what I could do is I could start to heat it. Maybe I could pass an electric current through it. And I could heat it, and pretty soon it would start to glow. And what color would it glow first, gang? Red. It would turn red. And then kind of red, orange, yellow, and then it would smear out to a white, become a white hot. And that means that what? The temperature is high enough so the radiation it's emitting can be seen. See, this is emitting radiation right now. But the temperature is so low. The temperature of iron is so low compared to that for incandescence over 1,000 degrees. The temperature of iron is so low that the radiation that's coming out doesn't activate your sense of sight at all. What you're seeing is reflected light from these hot lamps above, but not the light coming from here. But everything is emitting radiation. Question?
How fast does this radiation travel?
All this radiation travels at 300,000 kilometers per second. That's the speed of light. We know light travels that fast. It turns out that the heat rays, so-called heat rays, all electromagnetic radiation, 186,000 miles per second or 300,000 kilometers per second. Speed of light. And that's how fast these radiations travel. Everything's emitting and everything's absorbing. If something absorbs all it catches, then it reflects none. I'll show you an idea right here. There's a hole there. Is this hole absorbing the radiation that hits it, or is it emitting? I've got the color, I've got the inside of this box painted, gang. And guess what color it's painted?
Black.
What color does it look like now?
Black.
You've been reading the book, right? And we find out, lo and behold, it's white inside. Isn't that nice? Okay. But when I close the box, boom. Look into your neighbor's eyes, right in the very, very center. Do that right now. How many are shy? I said, no, I don't want to look in the eye. Come on, right in the eye. Come on. Right in the middle. Right in the middle. How many going like this? That's nice, isn't it? Isn't that nice? Hey, but how come the center of the eye is black? I mean, there's no reason for that. Everyone got black pupils. Why black pupils? Because they're like this. They're absorbing. They're absorbing. How much light that goes into your eye, bouncing around, how much do you think comes back out again? How much light that comes in here and goes through all this multiple reflections comes back out the hole? Not very much. So the hole to you looks black, okay? Because there's what? This is a net absorber. However, if I put a fire in here and made it very, very bright, then you'd see that hole very, very bright. Then it would be a net emitter. We call this a black body. A body that absorbs all the radiation that hits it appears black to the eye. We call it a black body. There's a whole science of black body radiation. We won't be getting into that. We talk about this temperature up here. How about like this? This is to say, if frequency is directly proportional to temperature, then if you double the temperature, what would happen to the frequency of radiation? Double. That's what it means when you write two things like this with a proportion. See, there's no square or cube or anything like that. That means one is proportional to the other. We've got that idea a long time ago, yeah? Okay? This says double the temperature, double the frequency. Well, let's suppose I consider something that's 1 degree Celsius. If something is 1 degree above freezing, would it be radiating energy? Would that energy have a frequency? Okay. How about I compare that to radiating at 2 degrees above Celsius? Would that be radiating energy? Would that energy have a frequency? Would that frequency be doubled? Check your neighbor. Yeah. Hey gang, would the temperature be, would the frequency be doubled? Get right to that point. Get right to that question. Question is, wouldn't that work best for Kelvin?
Yeah.
Honey, it will only work for Kelvin. Because 1 degree Celsius is not twice as hot as 2 degrees Celsius is not twice as hot as 1 degree Celsius. See, to say twice as hot is to imply twice the internal energy. Try this one. Waitress brings over some coffee because you've ordered coffee with your apple pie, and you says, "Oh, I'd like the coffee really hot." And she brings it over, and you put your trusty thermometer in it, and son of a gun, it's iced coffee, ice cubes and everything. It's 0 degrees Celsius. And you say to the waitress, "No, I know you're busy and all, but could you give me some coffee that's hotter than this?" She says, "How hot do you want it?" I said, "Well, I'd like to drink it twice as hot." What's the temperature of the twice as hot coffee if it's 0 Celsius to begin with? Okay, gang, in this case, I think you see that the Celsius scale doesn't work. Because twice as hot as 0 degrees. 0 degrees, there's still energy there, yeah? There's a lot of internal energy. And to say you have twice the internal energy, hey, 2 times 0 is what? Turns out 2 times 0 is 273. Let's be talking about that. We haven't talked about the Kelvin scale yet. We talked about the scales we talked about. We talked about the Fahrenheit scale, Fahrenheit degrees. We went from 32 to 212 for the temperature of boiling water and the temperature of melting ice. And we talked about 0 degrees and 100 degrees. And this was the Celsius temperature, or centigrade. Celsius, centigrade, same, okay. But now we have to talk about the absolute 0 of temperature when you start to take ratios of temperatures. Because this is not the coldest that one can get. You can get a lot colder than that. That liquid nitrogen we had in here the other day, that was about almost 190 degrees below this. How far down can you go? And it turns out, how far down you can go is 273 degrees down here. And down here on the floor, that is the absolute 0 down there. That's the absolute 0 of temperature. So it turns out on this Kelvin scale, we don't even say Kelvin degrees, we just say Kelvins. I mean, Kelvin was a real honcho, okay? It's all Kelvins, all right? On this Kelvin scale, the point at which ice melts would be 273 positive. See, on the Kelvin scale, there's no negative numbers. Everything is positive. Ain't that nice? Okay. And then the temperature of boiling water is 373 because they have made the Kelvin scale, the scientist types, so that it has the same divisions as the Celsius scale. But absolute 0 is 273 degrees under there. So if we have that iced coffee, or say, let's take something that won't change state, because it turns out the iced coffee, something will happen to it when it gets up to 100 degrees Celsius. What will it do? It'll start to turn into steam, see? But let's suppose you had like a piece of metal. I had this metal here at 0 degrees, and I make it twice as hot, twice the internal energy. See if your neighbor knows what would the temperature be in Celsius of this piece of iron bar, twice as hot as 0 degrees. Check your neighbor. Okay, gang, what's the answer? 273 degrees Celsius. Does everyone see that? If you don't see that, I think you can see it with this little story. Let's consider Celsius the village tailor. And Celsius is a tailor who has a shop, and he makes gowns for graduations. And he has a shop, and he has a ruler here, okay? And his ruler's right against the wall. Now, does that ruler have to have readings that go all the way down to the floor? It turns out it doesn't, because the shortest customer that tailor's going to have is probably about this high. And the tallest customer is probably about this high. So Celsius only need put sort of a measuring device from here to here. There's no need to go way down there, not for measuring the height of adults, people who graduate, yeah? So he starts here. All right, it turns out, by the way, that from here to the floor is 273 notches down, okay? Okay. Now, one day, someone comes into the store, and they get measured, and son of a gun, it's a little tiny guy like this, and Celsius measures the height and says, my gosh, you're right at the 0 mark. You're really, really short, aren't you? And the dude says, I got a sister twice as tall as me. How many notches tall is the sister? Do you see? You would say, now here we got 0 on the scale. Twice 0 is not 0. The sister must be, up to here. 273 notches higher. Do you see that? So we got to talk about kelvins. Kelvins. Whenever you're talking about something like this, nature's temperature. See, Celsius degrees and Fahrenheit degrees, those are people's temperatures. Nature's temperature doesn't start with a melting point of ice. Nature's temperature starts at the lowest possible temperature you can get to. You know, we talk about the energy of motion of molecules. Honey, at absolute 0, none. No more to give up. Things are at their rock bottom. That's the lowest temperature you can get. And so we always talk about things like this in terms of nature's temperature, kelvins. Some people in chemistry classes say, how come we got to convert to kelvins all the time? Well, if you're taking differences in temperature, you don't have to. But if you're taking ratios, you have to take nature's temperature, Kelvin degrees. Another kind of neat thing that is another common sense idea is Newton's law of cooling. This one makes sense. It has to do with the rate. The rate of cooling is proportional to delta T. In this case, I wouldn't have to be concerned with kelvins, because the difference in temperature from here to here and the difference from here to here would be the same, you see? I'm not taking a ratio. But over here, Newton's law of cooling is the rate of cooling is proportional to the difference in temperature. Now, what do you mean difference? You know, delta means difference. That means how hot something is compared to what the surroundings are. If this thing here is red hot, it's maybe something like a 500 degrees above the surroundings, then that's a high delta T. Guess what the rate at which those degrees are going to clip off will be? High rate. See? If I take this thing and warm it up a little bit like this, now it's a little bit warmer than the environment. How quickly does it cool? Not very quickly, because delta T is very small. If I put this in an oven and turn it red hot, take it outside, this thing starts cooling like mad. Okay? I mean, let's suppose every degree goes by you here. Click, click, click. Okay? Red hot. Click, 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 click. See? Warm, hot. Click. Click. Makes sense? It makes sense, doesn't it? Things that are very, very hot compared to the surroundings will cool off quickly. Things that aren't so hot don't cool off so quickly, huh? So that kind of makes sense. If you got a can of beer or something, you want to cool it down quickly. You put it in a fridge. Someone says, no, put it in a freezer. It'll cool faster. You say, well, honey, if it gets down to what the fridge is, that's good enough. I'll just leave it in the fridge. Who's right? Put it in the fridge or the freezer. You want to cool it faster. How many say, same? If you wait 5 minutes, the same. Check your neighbor. Do you kind of see that, gang? Do you kind of see that? In places where it's cold in the winter, when do those homes leak energy more? On a cold day or a warmish day? On a cold day, there's a greater delta T between the temperature inside the home and outside. And a great big delta T means, honey, you are going to have a high rate of cooling. And you know what you pay for when you heat your home? What you pay for, really, ultimately, is the heat that's leaking out all the time. Otherwise, you'd heat your home up in September, keep your doors all closed, you wouldn't have to burn any more fuel for the rest of the winter. But that's not true. The heat's leaking all the time, mostly through your windows. And the greater the delta T, the greater the difference in temperature between inside and outside, then the greater is going to be the rate of heat flow. And the opposite's true, too. If you're in a climate like around here, we are air conditioning all the time. The greater the difference in temperature between the outside and the inside, the greater the heat flows from the outside into your home, making your air conditioning bill goes up higher. So the greater the delta T, the greater the rate of cooling, or warming if you put it in the other way. It kind of makes sense, doesn't it? So that's a common sense type thing. This delta T is interesting. If you have small delta T, small changes in temperature, it turns out, I heard this some years ago, if you have a frog cannot discern small changes in temperature. If you put a frog in a pan of water, and then put that water on a hot plate, turn the hot plate on, and heat the water up very, very slowly, the frog will not discern the small temperature changes. And the frog, I heard, will just sit there and boil alive. I heard that. Being a science type, I had to try it. So at City College, I went up to the biology lab, 3rd floor. And I picked out a frog. Hi, Harry. And I put that frog in a little pan. Okay, hey, that frog, that's Auschwitz City up there anyway. That frog was going to get him right up in the head anyway, okay? I put that, and I made a deal with the frog. Froggy, if you survive this, I'll put you outside for the seagulls. I'll put you outside for freedom, all right? And I put the frog in there, and I put it in a hot plate, and I watched, and son of a gun, it was true. That frog was free to jump at any time. And the frog stayed there because delta T was very small, small, small. Now, if you heat it up very, very quickly, the frog would sense it and jump. But the frog got used to it. And then I heard this is not restricted to frogs. Guess what else behaved the same way, begin with P, and with eeple? Peoples. Yeah. People are the same way. You guys know that? If you get in a tub and someone heats it, this happened in Mill Valley. In Mill Valley in California a few years ago. A couple were sitting in their hot tub, and it had a faulty heater. And the heater kept heating and heating and heating, and the people just kind of got drowsy, and stayed right in there and cooked alive. Well, cooked dead, okay? Yeah, people the same way. As long as you make delta T small, you'll get used to it. You'll feel no pain, and you'll just kind of check out. This has an interesting application.
Is that true for the reverse, too?
Say again?
Is that true for the reverse when it gets colder?
I think the same thing is with colder, too. If you get gradually, you will accept it. You will become used to it. People are like that. We become used to all sorts of adversity if it's given to us in small enough doses. Like, name about anything you want, like sound in a factory. You could walk into a friend's factory and go in there and say, my God, how can it's so noisy? How can you stand it in here? You say, oh, well, you get used to it. When I came here, there was 2 machines going, and then 3, and then 4, and then 5, and you kind of get used to it. Of course, I can't hear anymore. Okay, that type of thing. Yeah, you get used to that. I had a friend from Japan, for example, come over to see me in San Francisco, and he saw all the bars on the windows. He said, what are all these bars for? I said, well, that's to keep the thieves out. He said, you guys are you got the bars on the wrong side. Why don't you put the bars around the thieves? Oh, no, the thieves have their rights, man, you know. He said, and the thing is, we get so used to it. First a bar on these windows, and then before you know, the whole city's a barricade. You know, something that happens slowly, you get used to and you accept. It's like the nuclear missiles, right? First a few, right? Then a few more, then a few more. Gradually, you live in a whole world ready to blow up, and well, you kind of get used to it. Small enough doses. Something happens in San Francisco at Fisherman's Wharf all the time that kind of bothers me. It's like Auschwitz there, Auschwitz. You get down there, you want to get your crabs, you want to get your lobsters. Or you go to Fisherman's Wharf and you want to order a nice lobster dinner. Now, what do you think that lobster you're eating, what do you suppose the fate of that lobster is before you eat it? They come out and say, hey, do you want this one here? And here's old Charlie, they're going like this, you know, hey, not me, right? And they're showing you Charlie. What do they do to that lobster? They boil that lobster. Now, is there any concern for the lobster's well-being? No. You want that lobster right away, right? You want it quick, because you got things to do. You know what they do? They take that lobster, open up a big pot of boiling water that's boiling, and they throw the lobster in. Let me ask you a question. What do you suppose the lobster thinks about that? What happened to that lobster when he goes to that? The lobster freaks. So you get your lobster comes to eat, right? And you look down at your lobster, and what's your lobster? And you're eating the lobster, looks like that. Why do they do that? Why not, and I'm serious, why not take the lobster and put it in water that's room temperature? Hi, Charlie. Bye, Charlie. No pain. Then put the lobster on the stove. Last time that's the way I cook lobsters. I do it that way. You put the lobster on the stove, room temperature water, then turn on the heat. Bring it to a boil, your lobster's cooked. You eating your lobster's a lot better. You're eating a happy lobster. I'm telling you, yeah. I don't understand that. Why freak out the lobster like that? What if there's a lobster heaven? You go, oh, what did you do to my kinfolk? Huh? Yeah, so cook your lobsters on room temperature water and bring it gradually to boil. Lobsters won't feel a thing. They'll be okay. Be eating happy lobsters. Lee, did you have a question?
In cases like this, wouldn't it be wiser to try to check your environment every once in a while just to make sure that you aren't boiling to death or something? Like if you're in a hot tub or one of these.
It's always good to check your environment to see what the delta T is, and the delta T could stand for so many things. Sure. Yeah. Hey, here's an easy question to answer, gang. No. Here's an easy question, not so easy to answer. Little kid says to you, so you live in Hawaii. Really nice. Nice and warm all the time. Yep, nice and warm all the time, man. I got some friends live up in northern Alaska. It's cold all the time. Well, that's the way Alaska is, man. How come it's so cold up there and so warm in Hawaii? And you say, well, there's no reason for that. Hawaii is tropical and Alaska's not. That's it. And the kid says, no, begging the question, why? And you say, why is it so warm here and so cold up near the poles? Is there a reason for such a thing? Check the neighbor. Well, that's easy enough. Hawaii is closer to the sun, further away. Is it true? Is Hawaii closer to the sun than Alaska? You guys know the closer and closer you get to the sun, the hotter it is? You know that? You know, you get within 1 million miles of the sun, the best materials you can make would vaporize. Not vaporize, but turn red hot. Well, maybe vaporize. You guys be knowing that? Unless you go at nighttime. But how about that? Is it true that Hawaii is closer to the sun than Alaska? Yes or no? Yes. Yes, that's true. Is it the reason? No, it's not the reason. Let's take a look and see if we can see why. Here's the Earth. Sunlight. Sun's way, way out there. Sun rays coming in. They fan out a little bit, okay? But essentially, they're parallel. They're coming in. Okay, now here's sun rays. Here's Hawaii down in here, and here's Alaska up here. Now, Hawaii is closer to the sun. But that's not the reason, gang, is it? Because let's suppose I take something like this eraser, and I put the eraser here. Boom. Let's draw it in here. So many acres of land. Now, let's consider the same acreage up north. See the reason already? Can you see the reason already? Even if you don't have the words, can you see, hey, yeah, over here you'd catch more energy than you would here. More energy per area here than here. This is one of those things that really makes sense, isn't it? Right? In fact, you can count them up. What do we got? 1, 2, 3, 4, yeah? And over here we got what? 1, maybe 2. So your energy is more concentrated here. Over here it's more spread out. The same energy over more area. So over here it's going to be colder, cooler climate. Over here, hotter climate. It kind of makes sense, doesn't it? That also tells us about the seasons, too. You know, it turns out, around here in Hawaii, you don't know too much about seasons. Well, let's talk about it anyway. Sun. Earth. Earth 6 months later. Turns out the Earth, see how we have it here? The Earth is tipped. Here's the polar axis going through here. So the Earth is tipped, okay? So that tip is about 23.5 degrees. That tip remains constant all around the Sun. So over here, it's like that, about 23.5 degree tip like this, okay? And 6 months later, the tip is the same. Has the same angular momentum here as over here, rotating about the same axis. That's our daily axis. Every day, how long does it take for this to turn one time? One time per day. We know that, right? So, but these are 6 months apart. Here's the equator. The equator. There's the sun. This is not to scale. But I'm going to label one of these. June or December. If one is June, the other is December. And you guys look and see which one he's going to put down June and which one he's going to put down December. Check with the neighbor and see what the neighbor says. Okay, gang, what'd you pick? How many say this should be December? How many say this should be June? Hey, the whole class. All right, you be knowing these things. Hey, okay. Yeah, it's going to be June, right? Because what happens in June? We're down in here. Look, we're catching more energy, huh? What happens 6 months later? Let's take a place that's up a little higher, about like San Francisco, or Denver, Colorado, or Oklahoma City, somewhere like that in the mainland, yeah? Let's look over here. Here they are in the summertime. They're getting the energy pretty flush in, yeah? 6 months later, over here. All right, now, here they are, but now it's nighttime. This part's the nighttime, isn't it? Wait 20, now here they are in the day, but look at over here. Ooh, they're only catching a little bit. People down here in Buenos Aires, they're the ones collecting all the energy, South America. That's why the countries down below, South America and Australia, in December would be having their summers, yeah? And we have ours just the opposite. That kind of makes sense, doesn't it? In the summertime, the Earth's tipped toward you, huh? Now, here's the old sun right here. Everything I can see, you guys can't get in back of me to see this, but I can see Amsterdam right there. All right. Now, Amsterdam, that's your halfway mark. Amsterdam is right in the sun. Okay, so it's day, 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 sundown, night, 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 sun up, day, 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 day. Get the idea? So they're in the daylight most of the turn. How about at a place that's on the daylight all of the turn, that's just barely on that? Of course, the North Pole is. Someone at the North Pole, daylight 24 hours a day. But you come down to a certain point where it just comes off. In fact, I can see right here, it's up here. And that point is called, anyone know? You guys don't know about it, it's too frigid. It's a circle. Begin with an A. Arctic, that's the Arctic Circle. The Arctic Circle is the point where you can get day for 24 hours a day on June 21st. Okay? June 21st, and the other ones where you get nighttime 24 hours a day. Because what happens when the sun's on this side? Okay? And here's where you get your long, long winter nights. Night, 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 night. And a very, very short day. So in the wintertime, very short days up the higher you go toward the North Pole. My brother lives in Costa Rica. In Costa Rica, he grows coffee. My brother lives in a place, Scout's honor, he lives in a place where there's no electricity. That's what he wills. He's living his childhood fantasy. He's living way, way out in the back hills there. Lives in a little finca, a little farm there, and he grows coffee. And last time I'm visiting my brother, he happened to mention to me that they have to import sweet corn. I said, why you got to be importing sweet corn? He said, well, we don't have enough sun. I said, you don't have enough sun? You got mangoes out the backyard there, you got guava trees, you got tangerines, you got grapefruit. What do you mean you don't have enough sun? You got plenty of sun. He says, no, brother, not enough hours of sun. Ah, hours of sun. Costa Rica, like Hawaii, about 12-hour days, 12-hour nights all year round. Isn't that true? We don't have a period where we have long, long days and short, short nights and vice versa. We don't get that here in Hawaii because you're at the equator and it's just about a half no matter where you go. It's only when you get up toward the pole you get the extremes. It's only up here where someone's in the nighttime all day long, okay? And then 6 months later, be in the daytime all day long, okay? It's only up here. Down in here, it's pretty well even all year round. So I thought that was kind of interesting. On the matter of saying that the closer one to the equator is the warmer one, that's like taking a couple of pieces of paper and holding them out in the rain. Let's suppose I hold these two papers in a rain like this, and they get wet, yeah? And a friend comes by, and I take them back in. And a friend looks at the papers, and the friend says, hey, gee whiz, this paper is wetter than this one. HC. I said, well, I don't know. Let me show you. And I go like this. Can you see why this piece of paper get wetter? And the friends say, oh, I see why, because this piece of paper is closer to the clouds. True? It is closer to the clouds, but that's not the reason. It has to do with the tilt, doesn't it? And does that tilt have anything to do with the seasons of the world? Does it? Think about that. You know why I want you to think about that? Because it's physics, A. All right? Boom.